Good morning. Thank you for being here with me. I know it's tough to get up this early, especially after the party last night. I personally struggle to do so. But don't worry. This talk is not going to be as complex as it seems. I try to make it as simple as possible, so I wouldn't screw it up even with the serious handover I have right now. Okay, let me briefly introduce myself. I am Xu Zikai. You can find me on Twitter and GitHub by my ID Bruce Xu. I am a student from National Zhongzheng University, and I major in computer science, currently on my second year of my master's degrees program. Well, this is a post I found a few days ago, which pretty much marks the time I began to write Rails. It was me, 2007. I was 11th grade student then. I've been using and loving Ruby ever since. Let us begin with a short story. There was a time when we programmers were happy. Well, at least relatively happier than we are. So, because even if we write some terribly slow programs, Moore's law tells us that our program will run twice faster in 18 months. Life was good back then. But the tide has changed dramatically when the chip clock rate hit the brick wall of physics laws. Manufacturer can no longer elevate the clock rate without burning the entire computer down. Therefore, they begin to build these new, shiny multi-core processors. And they claim the overall performance. The overall performance correlates to the number of CPU cores. Well, this kind of throws the problem back to us programmers. Since it's now all our fault if we cannot leverage the advantage of multi-core processors. So our good days are over. We need to adapt the parallel paradigm instead of the old sequential design. Unfortunately, this can be difficult and problematic at times. Let me give you a simple example. Let's say our programs manipulates a large list with 4 threads. Everything is all right in the ideal scenario. Each thread works just like they are independent from each other. But what if some of them try to modify the very same element? The result is unpredictable and likely to be wrong. These data synchronization issues are what make writing parallel programs hard. To deal with them, various mechanisms are developed. Among those, locking may be the most common one. Just like the name infers, the idea is to restrict the data from being changed by other possible access. A straightforward solution is to lock the entire list whenever a thread is using it. This guarantees that the list can never be modified. By others during the period of some thread manipulations. In other words, there's only one thread can use the list at a time. Well, doesn't that sound a little bit familiar? Yes, the biggest downside of this approach is that it literally becomes sequential execution again. So how do we solve this dilemma? Well, the key lies in the granularity of the lock. What we can do here is to divide a single coarse-grained lock into several fine-grained locks. In this case, we can place a lock inside every element instead of having only one for the entire list. Each thread now can freely modify any element it wants, unless it bumps into others that also want to modify the element. Only then will the execution order be in a first come, first served fashion. By now, you may be wondering about adapting parallelism on your existing Ruby script. If you already did so, you may find an interesting and surprising fact. No matter how many threads you use, no matter how well your design is, the official Ruby implementation, the MRI, will only use up one core of your processor. Okay. The reason we actually mentioned it a few slides ago. MRI uses a global interpreter lock to simplify data synchronization issues inside it. Let me quote what's on the Wikipedia here. Well, it's a kind of long, so I'm not going to read it. But as you can see, the idea behind all this is just like the first approach we introduced. The downside is pretty much just like I emphasized in this text. Even if run on a multiple processors, it always allows exactly one thread to execute at a time. So if you really want to make use of the rest of your processor cores, instead of maybe processor forking in MRI, most alternative Ruby implementation now use fine-grained locks, as far as I know. So JRuby, Rubinius, MacRuby, you name it. I don't know if Topaz, which built on PyPy, does the same, though. But there's one subtle problem of fine-grained locks I didn't mention earlier. Of course, we don't want to have a lock that is too coarse-grained, yet locks that are too fine-grained are quite likely to introduce some performance overheads. Since I can see maybe Charles here, so meanwhile I know little about JRuby, so let's take Rubinius for example, though. I have to confess that I also know little about Rubinius. Well, this is a chart from a benchmark on the internet. You can, yeah, there's URL, so you can follow it for further information. We can see from this chart that Rubinius 2.0 is significantly slower than the 1.2 version, which uses GIL. In certain benchmark scripts, once they test thread synchronizations, 2.0 was almost 70 times slower. Well, this is just a perfect example to show how difficult it is to have an adequate lock design. Besides that, using locks doesn't guarantee it's free from synchronization hazards. So let's look at this classic transfer between bank accounts. As we all know, transfer consists of two operations. First, we withdraw given amount of money from the original account, and then we deposit to the destination account. To avoid the account from being modified when we are performing these two operations, we lock the origin and the destination respectively. Well, while it sounds right, but we cannot be sure what will we get when we access these two accounts in maybe a small lockless window between actual withdrawal and deposit. The next thing come to our mind is to combine these two operations into one single transfer operation, and we lock both accounts during this transfer operation. Now it seems like our transferring program finally works correctly. However, the program will encounter another synchronization problem in a rare situation, that if both accounts is trying to transfer to each other. On doing so, both accounts will first lock themselves as origins, and the program will continuously fail to acquire the lock when they try to lock the destination account. So Simon Peyton-Jones wrote these 6 reasons of why locks are bad in his article, Beautiful Concurrency, in 2007. Therefore, the question has become that how do we have other choice rather than locking? Well, software transactional memory, or STM, may be one of the interesting alternatives to look into. It just borrows the concept of database transaction and applies it on memory manipulations. A modification on a variable is treated as a transaction. What is a transaction, you may ask? The original definition consists of these 4 attributes: atomicity, consistency, isolation, and durability, or ACID for short. Atomicity means that a transaction is either successfully committed or just about on failure. Consistency makes sure that the data we input in the transaction follows our integrity constraints. The isolation indicates that each transaction is independent, while durability requires the effect to persist after commit. So STM takes these attributes and transforms them to fit its need. Simply put, in most STM implementations, we initialize a transaction, execute it, validate it, and we commit. The result quite follow the atomicity attribute is either success or fail. The underlying implementation mostly uses locks, yes, but the way we execute a transaction makes it much easier and safer for us programmers to utilize. In short, I think STM provides some abstraction for programmers. Well, so the problem becomes, how do we implement STM in Ruby? You might ask. Well, think for a moment. I think I will ask you back. Why not in Go? And on the other hand, why not a new virtual machine? Well, I mentioned this name to my friends just few days ago, and many of them just tell me that this is a terrible name. Well, if you guys have a better idea, please get in touch with me, or just send maybe file an issue on the GitHub afterwards. Well, this is kind of embarrassing, I think. Well, I have to apologize for this. Since my cat has been pretty lazy lately, so I couldn't meet the deadline. He's the one to blame, not me. That's the reason why I'm not able to show you what it looks like, but I'm going to share some of the detail about it and hopefully see if there's someone who hopefully to see how you think about it. Okay, I guess many of you might ask, why Go? There's various reasons I chose Go over other programming language like traditional C, Rust, C++, or anything out there. First of all, although Go is a compiled static type language, it does learn something from our favorite dynamic languages, which makes it easier to pick up. Meanwhile, it still has a performance advantage over many major dynamic languages. And with support from Google, the community is expanding fast. Actually, I remember there's a GopherConf just right now, and maybe I heard about 700 participants. Well, then the fourth one is Go routines and channels. I will mention next slide. But I guess the most important reason is that writing Go makes you feel like a hipster instead of the geek. Okay, let's be serious. As I've mentioned, Go routines and channels are probably the most important features why I chose Go. You may see channels as message queues. One can pass a variable to a channel, and for any Go routines to pick up and process it. In my opinion, it seems like it's suitable for transaction dispatching. Let's go back to RunVM. It's designed as a subset of TinyRuby. Meanwhile, TinyRuby is a subset of Ruby, so it's a subset of Ruby. And the architecture of the VM itself is a stack-based machine. The bytecode mainly resembles what the YARF's instruction set. Therefore, the whole internal design is also similar to MRI, though it's relatively simpler and, meanwhile, less robust, I think. The last thing I have to say is I thank Ruby on the Microscope. The book is so awesome that makes the whole development process much less painful. Well, it's look I was a little bit speedy or whatever. Last but not least, let us just quickly scan through the basic algorithm of STM here. Transactional locking 2 is pretty much the basis of most STM implementations as far as I'm concerned. And the RunVM also uses, now you use TL2 as a fundamental algorithm to begin with. Maybe I'll switch to something later, but so far it's transaction locking 2. Well, the VM will maintain a global timestamp while each transaction has its own, which serves as a revision. If a variable is modified, its revision will be set to a global timestamp, as you can see from here. Translations also maintains a read and a write set. These two sets will record how each variable is used and classify it as to read or to write at commit stage. Reading, let's talk about reading. Reading is no big deal here, as long as the local revision is earlier than the local timestamp in each transaction. That pretty much shows that the variable is not modified. If the variable has been modified, the transaction will abort and restart all over again. For those in the right set, the transaction will acquire a global lock. Yes, you heard it, a global lock at a commit stage, then write the modified value back to the memory repository. So revision of each written variable gets updated meanwhile at the very same time to global timestamp. Oops. Oh, well, it's actually the same graph. So currently, the way RunVM handles such operation is pretty, well, let's say naive. It only creates transactions on encountering, say, maybe a thread block or something. For normal sequential segments, it stays in GIL mode, just like MRI did. Variables are copied into local transaction scope for manipulations. Since Ruby variables are basically all objects, the memory overhead is high in this manner. Well, above all, the system doesn't work correctly so far. So I think that, as you might say, that's the reason why I still keep this as a private repository. So anyone who likes to lend a hand or just to discuss RunVM with me, please feel free to catch me afterwards. Or you can just mention me on GitHub, on Twitter. Okay. I think that's probably it. Thanks for listening and enjoy the rest of the conference today. Thank you.